We're now moving on to the second part of materials, and we're going to discuss stress and strain. So essentially, a stress will cause a strain. How do we define stress? Well, it's the force applied per cross-sectional area. And a strain is defined as the change in length, i.e. the extension, divided by the original length of the material. And there we have the equations to mathematically express both stress and strain. And it doesn't really matter whether the forces are tensile or compressive, i.e. whether they stretch or whether they squash. The equations will be exactly the same. You just have to think of tensile forces as being positive and compressive forces as being negative. Now, a stress big enough to break a material is called a breaking stress. So if we plot stress against strain, we can see that the breaking stress is the point at which the stress becomes so great that the atoms separate completely and the material breaks. We also have something known as UTS shown on that graph, and UTS is the ultimate tensile stress, and that is the maximum stress that the material can withstand. Elastic strain energy. Now, this is the energy stored in a stretched material. So if you think about it, you have to apply a force to stretch a material through a distance, and therefore you do some work. Now, before you stretch it, the energy in the material is stored as potential energy. But after the stretch, some of that potential energy is converted into elastic strain energy. And if we plot a graph of force against extension, then the area under the graph will give us the elastic strain energy. If we take that a little further and we assume that the material obeys Hooke's law, then we have the following graph. And we can say that the work done is equal to the energy transferred, which is equal to the elastic strain energy, and that's the area under the graph, which then becomes quite easy to calculate. The energy is equal to a half multiplied by the force multiplied by the extension. And because Hooke's law is true, we can say that F equals KE. So if we substitute that into the equation above, we have that the elastic strain energy, or the work done, is equal to a half KE squared. Moving on now to Young's modulus. Young's modulus is denoted by the letter capital E, and that is stress divided by strain. We already know the equations for stress and strain, so if we combine these, we can see that Young's modulus is equal to the force multiplied by the length of the material that it is originally, divided by the cross-sectional area of the material multiplied by the extension. And in this diagram we can see the equipment that you would use to conduct a Young's modulus experiment. Moving on to interpreting stress and strain curves. Well, again, we've got stress plotted against strain. We can see the limit of proportionality, which is the point at which the material stops obeying Hooke's law and the graph no longer becomes a straight line. And then we have the elastic limit, and beyond that point the material will start to behave plastically. The yield point is the point at which the material suddenly starts to stretch without any extra load being applied. And then we have the ultimate tensile stress, which, as mentioned earlier, is the greatest stress the material can withstand. And finally, the sample will break at the breaking stress. And if we look at a material such as glass, we'll find that the graph looks somewhat different. These materials just break suddenly, they do not deform plastically. Well, why is this? Brittle materials have a rigid structure with strong bonds between the atoms. For example, ceramic has a giant rigid structure. So when you apply a stress to a brittle material, any tiny cracks in the surface of that material just get bigger until the material breaks completely. And that is known as brittle fracture. And this concludes the end of the section on materials.
Created using Powtoon.